Hello everyone, welcome to the lecture series on IC engine. I am Professor Anuranjan Sharda from GNA University Fagwada. Today we will be talking of performance parameters of IC engines. Now the learning objectives of this presentations are: students will be able to recognize and define various performance and operating parameters of IC engines, comprehend the parameters affecting the engine performance and fuel consumption, identify the design parameters of IC engines which ensures the economic utilization of engine space and size. In this, we'll be discussing the efficiencies of IC engines, including combustion efficiency, thermal efficiency, mechanical efficiency, volumetric efficiency, and air-fuel ratio, stoichiometric air-fuel ratio, the specific fuel consumption, including both the brake-specific and indicated specific fuel consumption. The design parameters will also be discussed. Let us start with our first slide, that is efficiency of IC engine. Now, efficiency is the relation between the power delivered and the power that could be obtained if the engine operates without loss of power. There are three types of engine efficiencies: combustion efficiency, thermal efficiency, mechanical efficiency. In addition, we also have the volumetric efficiency. So we'll be talking of the combustion efficiency first. Now, as the time available for combustion is very short, a small fraction of fuel does not react and exits with the exhaust flow. That means the mass of the fuel completely do not burn. Some of it exits with the exhaust flow. So a combustion efficiency is defined to account for this fraction of fuel which is burnt, and typically has the value in the range of 95 to 98%. Now it is defined as Q, input heat which is given to the engine, can be defined as mass flow rate into its calorific value into the combustion efficiency. So hence the combustion efficiency can also be defined as the ratio of actual heat input divided by the heat which is expected to be generated by burning a fuel of mass mf depending upon its calorific value. Thermal efficiency is the ratio of power produced to the energy supplied by the fuel. Now power produced is denoted by P, and the energy supplied by the fuel can be written as mf into CV, as CV is the amount of energy which is produced per unit mass of the fuel. Depending upon whether it is brake power or indicated power, this thermal efficiency can be written as brake thermal efficiency or indicated thermal efficiency. So hence two expressions are used. One is BTH, neta BTH. It is defined as ratio of BP upon mf dot into CV, and neta ITH, which is defined as indicated power upon mass flow rate of fuel into calorific value. Now next parameter is the mechanical efficiency. Mechanical efficiency measure how efficiently power produced inside the cylinder is transmitted to the crankshaft by the mechanical components. It can be written as the ratio of brake power to the indicated power. Since brake power is the power available at the crankshaft and indicated power is the power produced inside the engine, so indicated power will be of greater value as compared to the brake power. Hence this ratio will be in fractions. Multiplied by 100 gives you the mechanical efficiency. So mechanical efficiency usually lie between 80 to 90%. It can also be defined as the ratio of brake thermal efficiency to the indicated thermal efficiency. As we know, brake thermal efficiency is the ratio of brake power divided by mf dot into CV, and indicated thermal efficiency is the ratio of indicated power divided by the same amount mf dot into cv. So mf dot into cv will cancel out and you get the ratio bp upon ip, which is nothing but mechanical efficiency. Similarly, you can also write it in terms of indicated specific fuel consumption and brake specific fuel consumption. This relation, this parameter of specific fuel consumption we will be discussing in the coming slides. First we talk of air fuel ratio. Now what is air fuel ratio? It is the ratio of mass of air to the mass of fuel, which is sent into the SI engines to get the mixture and which is burned to give us the power. It can also be defined in terms of rate of mass flow rate, that is mass flow rate of air divided by mass flow rate of fuel. SI engines may have air fuel ratio in the range of 12 to 18. So based on the load conditions such as starting, accelerating, cruising, etc. Whereas CI engines, they have a air fuel ratio in the range of 18 to 70. So it's a wider range. So hence CI engines, they are generally used for heavy vehicles so that it can cover the wider range of accelerating, starting, cruising, etc. Next is the stoichiometric air fuel ratio. Now what is stoichiometric? Stoichiometric is a term used for a chemically correct mixture. Chemically correct means the amount of substance required to completely react with the other substance is exactly the same. So hence in this, the mixture that contains optimum proportion of fuel air ratio, like all the fuel will completely burn with all the air present inside the carburetor. Now equivalence ratio we define. Equivalence ratio is the ratio of actual fuel air ratio divided by chemically correct, that is stoichiometric fuel air ratio. So if the actual fuel ratio is chemically correct ratio, so this ratio will be equal to 1. So phi is equal to 1 for chemically correct ratio. So phi is less than 1 for lean mixture, because the actual fuel air ratio will be lesser than the chemically correct fuel air ratio. Similarly, phi will be greater than 1 if it is a rich mixture. For SI engine, the air fuel ratio varies from 12 to 18, and for CI engine it varies from 18 to 70. Now you can see here, we can also write, instead of writing it in ratio air to fuel, you can also write it in fuel to air terms. In that terms, you have 0.056 to 0.083 range for SI engines and 0.014 to 0.056 range for CI engines. Next is the volumetric efficiency. So volumetric efficiency represents the amount of charge that we are sending inside the cylinder. The power of output of an engine directly depends on that amount. So this is often referred to as the breathing capacity of the engine also, and is expressed quantitatively as volumetric efficiency. So it is defined as the ratio of actual volume of air induced to the swept volume. Now swept volume is the maximum volume which can be contained by the engine. Maximum volume of charge that can be contained by the engine is represented theoretically by the swept volume. So it is written as neta V, that means volumetric efficiency, is equal to MA, mass of actual air sucked in, divided by rho A VD. Rho A VD is representing amount which is going, mass flow rate which is going inside the cylinder. So neta V can be written as NMA dot divided by rho A VA N. Capital N is the engine RPM, and small n is the number of revolutions per cycle. That means in a complete cycle consisting of suction, compression, expansion and exhaust stroke, how many such cycles are completed in one revolution? Volumetric efficiency can be defined as the ratio of actual mass of charge inducted divided by theoretical mass of charge inducted. Now this theoretical mass will be greater than actual mass, so hence volumetric efficiency will be obtained after multiplying this fraction with 100. Actual mass is always less than the theoretical mass because of pressure losses in the ducting system and due to the heat transfer, since the process is not adiabatic. Volumetric efficiency for a normal engine is about 80%, and this value can be increased by supercharging or turbocharging method. Supercharging means we are adding the more charge than can be kept by the naturally suction of the engine. That means it is not naturally aspirated. We are sending the charge by compressing it into the cylinder. So this supercharger is basically a compressor which is run by the power from the engine only. Whereas turbocharger, it's also a compressor, but it is run by the exhaust gases moving out of the engine. It's run by a turbine which is in turn run by the exhaust gases. Now improving the volumetric efficiency. So volumetric efficiency of an engine can be improved by modifying the intake passages. How we can modify? Like shown in this figure, you are having a curve here. So you can see the dotted lines. So this earlier dotted line, it was say having a sharp curve. So what we do, we flatten it so that it becomes very smooth movement for the induction charge. Similarly here, it was having this sharp end. So it was also eliminated, and you are having now no constriction to the movement of the charge, right? So hence you can modify the intake passage to make it easier for the mixture to flow. Other changes include reshaping ports to smooth bends. So you are having this port, so you are having a smooth bend here. Then reshaping the valve heads, you can see this. This was the initial dotted line is representing the initial construction of the valve. So it was a little undercut was made here so that you have a greater amount of flow of the charge around this valve. And last is the polishing inside of the ports. So you can see here smooth port walls. So smooth port walls are made by polishing this area so that friction is reduced and hence more air and mixture flow can take place. The next we'll be talking of volumetric efficiency of two-stroke engine. Now for the same power generation, air input of two-stroke engine is greater than the four-stroke engine. Why it is greater? Because it requires scavenging also to be done. As there is a loss in the scavenging period, the term volumetric efficiency is replaced by the term delivery ratio and charging efficiency. So what is delivery ratio and charging efficiency? So delivery ratio is the ratio of charge inducted divided by maximum charge that could have been inducted. Now how much amount of charge is inducted? It is represented as Mi, and how much amount of maximum charge which could have been inducted, that represents the stroke volume. So stroke volume into the density of the charge, that gives us the maximum charge that could have been inducted. Similarly, we define the other term, charging efficiency. Charging efficiency means charge which is trapped. Now what charge is trapped? Because when the scavenging takes place, some of the inlet charge also moves out from the exhaust valve along with the gases. So, but most of the charge is retained. So, the charge that is retained inside, that is called charge trapped, denoted by MT. So, mass of charge which is trapped is represented by MT. So, ratio of MT with that of MC, that is the maximum charge, that is called the charging efficiency. Now, since delivery, some of the mixture is lost out of the exhaust port before it is closed, so delivery ratio will always be greater than charging efficiency. Next parameter that we use in volumetric efficiency of two-stroke engine is the trapping efficiency. As the name suggests, it measures how efficiently fresh charge is trapped. So this is the amount of mass which is being trapped inside, that is MT, divided by total mass which is contained inside, that is inducted. So MT upon MI gives you the trapping efficiency. Similarly, scavenging efficiency represents how efficiently fresh charges scavenges the exhaust gases. So here it is the ratio of charge which is trapped divided by the total charge. Total charge means the charge plus the exhaust gases, right? So some of the exhaust gases, they also remain inside. So hence this is the total charge, the charge which is trapped. Then the final ratio is called relative charge. So it is represented by lambda RC, and it measures how efficiently cylinder is filled with fresh charge and exhaust residual as compared to its theoretical maximum. So it's the ratio of mass of total charge trapped divided by the maximum which could have been trapped. So you can see here from these two ratio, if we divide this charging efficiency with the scavenging efficiency, we get the relative charge. Next is interrelationships of these volumetric efficiencies. Now you can see here charging efficiency represented by the trapped charge divided by the maximum charge can be represented as the product of delivery ratio and trapping efficiency. Delivery ratio is how much of the inducted charge, the total charge, how much of the maximum charge the charge is inducted, Mi divided by Mc. Whereas trapping efficiency is how much charge is trapped out of the maximum charge which could have been attained. So maximum charge cancels out and you are left with Mt by Mc, which is nothing but the charging efficiency. Similarly, charging efficiency can also be written in terms of product of relative charge to scavenging efficiency. So relative charge is again the total charge which is trapped divided by the maximum amount which can be contained in the engine, MTC by MC. So hence similarly, scavenging efficiency can be written as MT upon MTC. MTC cancels out and you get the charging efficiency. So here are some typical values of this charging efficiency and delivery ratio, etc. So for delivery ratio, it varies from 0.65 to 0.95. For charging efficiency, it varies from 0.5 to 0.75. For total charge, it represents from 0.65 to 0.8. From scavenging efficiency, it varies from 0.75 to 0.9. And for relative charge, it varies from 0.6 to 0.9. Then we talk of specific fuel consumption. Now, when we say we are having two different engines, one is of 50 horsepower and the other is of 5 horsepower. Now, we can't compare the fuel consumption which is being made by each of the engine, because it is clear that 50 horsepower producing engine will consume more charge. So fuel consumption cannot be used to compare two different engines. So hence we define another parameter called specific fuel consumption. It tells us how much fuel rate, the fuel flow rate is required for producing 1 unit power of output. So hence SFC is equal to mf dot divided by P. So depending upon whether it is brake power or indicated power, we have the terms BSFC, brake specific fuel consumption, and ISFC, that is indicated specific fuel consumption. BSFC is written as mf dot, that is mass flow rate of fuel, divided by brake power. ISFC stands for mf dot divided by indicated power. Now SFC is a measure of how efficiently the fuel supplied to the engine is used to produce power. Clearly a low value of SFC is desired. So hence, because we define mileage on this value, SFC, specific fuel consumption. So we can compare if 50 horsepower engine is better or 5 horsepower engine is better by conducting the by carrying out measurement of SFC, specific fuel consumption. That is how much fuel will be consumed by each of the engine for producing the same power, that is 1 HP. Next we talk of brake specific fuel consumption versus engine size. Now you can see this graph. From here it is clear that BSFC decreases as we go on increasing the size of the engine. Size means the displacement volume of the engine. So BSFC generally decreases with engine size due to reduced heat loss. Why it is decreasing? Because the heat loss from the gas to the cylinder wall is decreasing by increasing the size of the engine. Now note that cylinder surface to volume ratio increases with bore diameter. Cylinder surface area can be written as internal surface area it is. So it can be written as 2 pi r into L, whereas cylinder volume can be written as pi r square L. So LL cancels out, RR cancels out, pi cancels out, and you are left with 1 by R. Now 1 by R, it is proportional to 1 by R. 2 is a constant, right? So this ratio is proportional to 1 by R. So as we increase the R, what happens? This ratio, surface area to volume ratio, it decreases. So due to this decrease, the heat loss also decrease, because heat loss is directly proportional to the area which is available for the heat. Next we talk of variation of BSFC with engine speed. So what we have shown this graph, you can see as the engine speed increases, this specific fuel consumption, brake specific fuel consumption, it decreases and is reached to a minimum speed around say 3200 RPM, and from there it starts again increasing. Now what is there, that at lower speed and at higher speed specific consumption are maximum. Now you might have seen on your speedometer of your bike or car, there is a economy range in which if we run the engine, we will be getting the maximum mileage. So here that thing is clarified. Now why is it so at lower speed you have high brake specific fuel consumption, at higher speed again you have high specific fuel consumption? This is because at lower speed, since the piston movement is slow, so hence there is a greater time available for the heat to be dissipated through the cylinder. So hence losses are more. So hence the fuel consumption, it is more for producing same power. Whereas in case of when the speed is higher, what is there? The piston moves with a greater speed and hence the friction is more. So here frictional power increases. So in the high speed, the fuel consumption increases due to the increase in the friction losses, whereas at lower speed, the this BSFC increases due to the increase in the heat losses. Next, there are some other design parameters. First one is the specific weight. So specific weight, it indicates the relative economy with which materials can be used. So how the weight with power is varied. So engine weight divided by engine power will give you the specific weight of an engine. So power can again be brake power or indicated power. If we take brake power, it becomes brake specific weight. If we take indicated power, it becomes indicated specific weight. Similarly, for specific volume, it indicates the relative effectiveness with which engine space is utilized. So it is the ratio of engine volume to the engine power. So given as VD upon BP, VD stands for displacement volume, BP stands for brake power. So similarly, again, we can have brake specific volume or indicated specific volume of an engine. The third parameter is specific power. It measures the effectiveness with which the piston area is used, regardless of the cylinder size. So how effectively we use the piston area. So it is the ratio of engine power to the piston face area of all the piston. So like we are having 3 cylinder, so we will be talking of piston face area of all the 3 cylinders. Thank you for today. So we'll be discussing in the next lecture series, we'll be talking of how we can measure the different parameters that we have studied so far. Thank you.